Good day, everyone. Welcome to the continuation of our lecture series on our course Physics 2. Today's discussion involves the concept of electric potential and electric potential energy. This topic would set the stage for our further discussion on electricity and basic electronics. Okay, so today's coverage would involve the following topics. We have number one, electric potential energy in a uniform field, electric potential energy of 2-point charges, electric potential energy of several point charges, and finally, the idea or the concept of the electric potential. Okay, so let's start off with the first topic, electric potential energy. Okay, so recall in your physics 1 that when a force acts on a particle here could be represent or could represent any object that receives a force, and that force acts on that particle and causes that particle to move, for example, from 2 points between point A and point B. Then let us recall the idea of the concept of work. If you're going to recall the idea of work, the work is basically the product between force and displacement. Uh, Although you see here that the work is equal to the a complicated expression here, we call this expression an integral form of the product of the force and displacement. But in simplest terms, you need not to worry. You need not to worry about the form of the equation, because we will not be dealing. Our approach on our discussion on physics 2 is not calculus based but algebra based. So in a direct sense, we will actually do away with the mathematical form of this of the discussion in calculus. So our approach should simply be in algebraic form. So what I'm going to present to you is, or if you're going to recall, the algebraic form of the work done, that the work done is the simply the product between the force applied on an object uh, multiplied by the distance uh, covered by the object if that object has been successfully moved by this force. Okay, so the idea is the force and the distance should be in the same direction. If for practical purposes, if you're going to recall or try to do it yourself, for example, if you try to apply a force on any object, um, for example, if you're holding your mouse right now, so for example, if you move the mouse forward, that means you are applying a force. So we know that you are actually moving your mouse. If the cursor of the on the screen is actually moving upwards or downwards, so that means you're applying a force. You're actually moving the mouse in the forward direction. So try to notice that when you move the mouse forward, that the distance covered by the mouse is in the same direction as the force applied. So the idea here is that the work done produced by the application of the force and the displacement of the object should be in the same direction. Otherwise, if the force and the displacement are not exactly in the same direction, then the definition of the work done is simply we get the component of that force along the direction of the displacement. That is why there is a second form of the formula for the work, wherein we have force times cosine of the angle in between the force and the displacement multiplied by the displacement itself. Okay, so again, you need not to worry about the form of the equation. So our approach later on, especially when I will be presenting to you the examples, our approach would be algebra approach instead of calculus. Okay, so the work done by a force, where the dl here, or L, simply represents the displacement or the distance covered by the object upon the application of the force. Okay, so the angle here represents the angle between F and the displacement. So just as you can see here, the other form of the work done is in algebraic form, not in calculus form, as we can see in this expression. So mostly in the succeeding examples, we will be using this form of the equation, which is in algebraic form. Okay, so if the force is a conservative force, the work done by F can always be expressed in terms of the potential energy U. When the particle moves from a point where the potential energy is U sub A to a point where the potential energy is U sub B, then the change in potential energy, which is represented by delta U, U sub B minus U sub A, or the final amount of the potential energy minus the initial amount of the potential energy, and the work done from A to B by the force is given by the work done by moving the object from A to B is given by negative delta U, which is negative U sub B minus U sub A, or if you're going to distribute the negative sign inside the parentheses, we will have U sub A minus U sub B. Okay, so let's try to analyze first, or try to recall first the following ideas before we proceed further. Okay, so try to recall that this concept is not new, since this is supposed to be physics 2, so it is assumed that you already know the concept of the work, since it is also assumed that this topic was already covered in your physics 1. Okay, so let's try to go over the concepts again one by one. Okay, so let's start with the first sentence. If the first condition, if the force is conservative. So what is meant by a conservative force? A conservative force is a type of force when you apply that force actually conserves the corresponding amount of energy involved in the application of the force. It is as opposed to non-conservative forces, wherein non-conservative forces are type of forces which dissipates the amount of energy of a system. What is meant by the word dissipates is the word dissipates refers to the force causes a decrease in the amount of energy. Now, when we talk about conservative forces, these forces can decrease the amount of energy, but that amount that was decreased, if you apply again a force in the opposite sense, you should be able to retrieve that amount of force without any change in the amount. So whatever you have taken for a given amount, you can always return it back. So that type of force, we call this force as a conservative force. An example of a conservative force is the force of gravity. So for example, if you try to throw an object upward, so the tendency is as the object goes upward, the object actually gains a certain amount of potential energy. Once it reaches its maximum height, what happens is that gravity would always pull it back downwards, back down to Earth. So the amount of increase in the potential energy before when it was going upward would eventually decrease, going back to its original value from where the object started its flight, thus decreasing the amount of potential energy. This amount of potential energy decrease is equal to the amount of energy increase when the object is actually going upward. So that means basically there is no change in the amount of energy in the system, because basically the force of gravity is a conservative force, or simply what is meant by conservative force again is that this is a type of force that can increase or decrease a system, but without diminishing the amount. It can return the amount of energy lost in the system by simply getting the opposite sense of the direction of the force. As opposed again to non-conservative forces. Non-conservative forces are forces that dissipates the amount of energy, and that is what is meant by dissipate, is that it can decrease the amount of energy without being able to return that amount that was decreased. Okay, so I assume that you already have taken this in your physics 1, and this is a basic concept in physics 1. If you're having difficulty in understanding or recalling the ideas of work and energy, I suggest that you review those parts, those topics in your physics 1. Okay, so at the moment, since I am assuming that you already know this part of the concept in physics, I will be proceeding with this assumption that you already know this concept. Okay, so again, our definition is that the work done by the applied force in moving the object at point A to point B is equal to the negative change in potential energy. This is the negative change in potential energy of the object. Okay, so again, just to add additional concepts, what is meant by the negative sign here is this indicates whether the system is increasing in amount of energy or decreasing. Remember that when in our example, when you throw an object upward, what happens in terms of the movement of the object is actually moving upward. So in terms of the direction of the displacement is going upward. Whereas the force of gravity is always downward. So that means in terms of the direction of the force and the displacement, they are actually opposing. So what is meant by this opposing direction between the force and the displacement? It means that when as the object goes up, and the amount of associated potential energy is actually increasing. So that means if you have a negative force or a force and the corresponding displacement opposing each other in terms of their direction, it is accompanied by an increase in potential energy, and thus the sign of the work done is actually negative. So when you have a negative force, you actually have an increasing potential energy, and that means that the force and the displacement are in opposite direction. Okay, so on the other hand, positive work means that in the opposite sense is associated with a decrease in potential energy. And in terms of the sign of the work and the displacement, it follows that the force and the displacement should be in the same direction. So as in our example of the object thrown, when the object reaches its maximum height and eventually gravity would take over, pulling the object downwards again. So what happens is during the flight of the downward movement of the object, the direction of the force and the displacement is both going downward. Therefore, they are in the same direction. And it follows as the object goes down, what happens to the associated amount in potential energy is that the potential energy decreases. So it follows, since the direction of the force and the displacement are of the same direction, the sign for the work done would be positive. So that means a positive value of the work done is associated with a decrease in potential energy. Okay, so I hope that you get that. If you're not able to get that, you could always rewind the video lecture and go over the concepts again. Okay, so let's try to illustrate further. The work done in our example is as illustrated here. You have a baseball that is moving across a uniform gravitational field. So you have a baseball moving across this path between points A and point B. So what is meant by this path is that it doesn't matter whether the ball travels this path or whether the ball travels this path or whether the ball simply goes straight from point A to point B. So the point here is regardless of the path taken by the ball, for as long as the ball started at point A and ended up at point B, the work done in moving the baseball from point A to point B is the same regardless of the path. So whether the object or the ball moves along this path or simply goes straight from point A to point B, the amount of work done in moving the object at point A to point B is the same all throughout. This means that the associated potential energy is doesn't depend on the direction of the movement of the object, but is independent of the direction. Uh, it follows if potential energy is independent of the direction, therefore potential energy is a scalar quantity and it does not have any associated direction. Just like I assume that you already know this from your physics 1. Okay, so the work done by the gravitational force is the same for any path from A to B. The work done from A to B is equal to the negative change in potential energy equal to the product of the mass of the object times g times height. This part of the discussion is actually review of physics 1, and this would set the stage of understanding the application of work in electricity. Okay, so let's now proceed with its analogy with electricity. The analogy of gravity with electricity. Okay, so we have electric potential energy in a uniform field. Okay, so just like what we have seen in the example for this baseball, instead of having a baseball, we'll have a charge that is within a gravitation within an electric field, which was set up by two electrically charged plates. The upper plate is positively charged. It is positively charged because it has deficiency in electrons, and the lower plate has negative charge because it has an excess of electrons, making it more negative, and the upper plate making it less negative because of the deficiency in electron, setting up this electric field in between. Now the indicated line for the electric field is this one, the colored pink. It indicates a uniform electric field because of the straight line direction of the arrows representing the field. Okay, so the idea here is that from the charge moves from point A to point B. So just like since of course the field acts on our charge, if the sign of our charge is positive, and the tendency, since this would be positive and the upper plate is positive, since they are both positive, the tendency is that the upper plate would actually would push the positive charge downwards, in the same time that the lower charge attracts our positive charge since they are in opposite signs. So the upper plate would push the charge downwards, at the same time the lower plate would attract the charge downwards, so the overall tendency of the charge moving from point A to point B is towards this direction. Now, perhaps our charge Q sub O here does not follow a straight line. It could possibly that the charge would follow a different path, just like what is represented here by the dashed line. But the point here is, for as long as the charge started at point A and ended up at point B, then the amount of work associated in moving the charge from point A to point B would be equal to the change in potential energy, but this time it is no longer gravitational potential energy, but we call this the electric potential energy. So that means if we are going to try to make an analogy between gravity and electricity, the downward electric field is just like the downward effect of gravity, and the pull of gravity is like the pull of the lower plate and the push of the upper plate on our charge. Thus, we have a charge that is going downwards by the natural effect of the electric field, just like we have the natural effect of gravity of pulling every object going downwards towards the earth. So I hope you get the analogy. Try to review this again, this basic analogy, because we will always compound on this idea of the analogy between gravity and electricity. Okay, so now the question is, what would be the amount, the work done of the electric field on our charge as it moves from point A to point B. So we have already established from the previous discussion that the work done associated in moving the object from point A to point B is equal to the negative change in potential energy due to gravity. Now, since we have replaced the gravity, instead of using gravity, we gravitational field, we make use of the electric field. So therefore, the amount of force here, the amount of work in moving the object from point A to point B is equal to the negative change in potential energy, but this time this potential energy is no longer gravitational potential, but it is electric potential energy. Okay, so how do we now compute for the potential energy of the associated with the movement of the charge from point A to point B within the within the electric field? Now, try to notice the um, analogy between electricity again and gravity. Here is the electric force. In our previous example, the force is actually the weight, which is the force of gravity. Now, this is in our computation of the weight of the object, which is the force of gravity. We determine the weight using Newton's second law as the product of the mass and the acceleration. If you try to recall this in your physics 1, so the weight is equal to the product of the mass of the object, the mass of the ball, times the acceleration due to gravity. Now, although we define this as the acceleration due to gravity, but actually in the sense of the gravitational field, the acceleration due to gravity is actually a measure of the amount of the effect of gravity of that at a certain location within the gravitational field of the Earth. Therefore, this G is actually a measure of the strength of the gravitational field of the Earth. So it follows, by analogy, weight corresponds to our F, G corresponds to our E. It follows that M corresponds to our Q sub O. F is the weight, this one. G is equal to the electric field. G is the gravitational field. E is the electric field. And Q sub O is the representation for M by analogy. This is gravity. This is electricity. Now recall, our definition for work is equal to the product of the force and the distance, or the displacement of the object. So if the displacement of the object is represented by d, the distance between point A to point B, then it follows that the negative change in potential energy is simply the combination of the analogy of quantities between electricity and gravity. We have Q sub O times the electric field times the distance. Since this is the force, this is force times distance, or displacement. Remember, our definition for work is force times displacement. This is the force, Q sub O times E, then this is the displacement. And this is equal to the negative change in potential. So again, let us recall. In gravity, the negative change in potential energy indicates whether the system is of increasing amount of energy or decreasing. Remember, in our previous discussion, I have mentioned a while ago that when the work done is negative, it is associated with an increase in potential energy. If the work done is positive, then it is associated with a decrease in potential energy. So the same goes with electricity. The only difference is that you have a gravitational field before, but this time we have an electric field. Okay, so in the previous figure, a pair of charged parallel metal plates sets up a uniform downward electric field. with magnitude E. The field exerts a downward force with magnitude F is equal to Q times E. The work done by the electric field is given by, of course, work is force times distance. Work is equal to force is Q times E times the distance. Uh, Okay, so I'll be skipping this first, the introduction of the letter V here. We will be discussing this for along the way as we progress with the topic. So at the moment, we just suffice we just be dealing with the discussion on work up to this point only. Okay, so let's have a sample problem. Okay, so a proton with charge positive E moves in a straight line from point A to point B inside a linear accelerator, a distance of 0.5 meters. The electric field magnitude is 1.5 to the 7 Newton per Coulomb in the direction from A to B. Okay, so determine letter A, the force on the proton. Letter B, the work done on it, and letter C, the potential difference. Okay, so I have not yet discussed the idea of the potential difference. I will be discussing this along the way. Okay, so I'll be showing you now the solution for this problem. Let us apply the um, the previous discussion on the problem. This is the same problem, and this is the corresponding illustration. So just like what was described in the problem, you have two metal plates, the upper plate and the lower plate. The upper plate is positively charged. The lower plate is negatively charged. The charge of the strength of the electric field in between the two plates is given by 1.5 to the 7 Newton per Coulomb. And you have a proton, which is positively charged, of course, traveling from point A to point B, and the distance in between point A and point B is 0.5 meters. So the question is, how much force was experienced by the proton as it moves from point A to point B? Okay, so just like what we have discussed before, the force is simply equal to the product of Q sub O times E. Remember in our discussion on Coulomb's law, the introduction or the electric field, the electric field can be found by the ratio between the force over your test charge. So this time, our test charge is our proton, and solving for force instead of the electric field, we have force is equal to Q sub O times E. Okay, so the letter A is simple direct substitution problem, so we just substitute directly the given corresponding values. Okay, so we have the charge of the proton, Q sub O. Remember the basic elementary charge is the charge of the electron, and the charge of the proton is the same, 1.6 positive 1.6 to the negative 19 coulombs for proton, negative 1.6 to the negative 19 coulombs for electron. So we have a proton here, so we have positive 1.6 to the negative 19 coulombs. We multiply that with the strength of the electric field, you have 1.5 to the 7 Newton per Coulomb. Okay, so multiplying these two, you have 2.4 to the negative 12 newtons. Okay, so we have answered letter A. Now next is letter B. What is the work done on the proton as the proton moves from point A to point B? Okay, so the basic formula for work is equal to force times distance. Since we already computed for the force, so that is 2.4 to the negative 12. Multiplying that with the distance traveled by the object from point A to point B, the distance between is given in the problem, that is 0.5 meters. So that is 0.5 meters here. Multiply that with 2.4 to the negative 12. We have the work done as 1.2 to the negative 12 joules. Remember your unit for work. The unit for work is the unit for energy, which is the joules. That is spelled as Joules. Okay, so next in our problem, we are asked to get the potential difference. Okay, so before we proceed with the computation, let me go through with the corresponding concept of the potential or the potential difference. Okay, so first, Recall that work is equal to the negative change in potential. And the negative change in potential is equal to the negative change final minus initial. Final is the potential energy at point B. Initial is the potential energy at point A. So this is, remember, whenever you are asked to get the change or the delta between a the delta of a quantity, it is always final minus initial. So final u sub B minus initial u sub A. Now, of course, we can distribute the value of the negative sign inside the parentheses, so that reverses the position of point A and point B. Okay, so of course, there, based on our previous computation work, the value of the work done is 1.2 to the negative 12 joules. This is equivalent to the difference between U sub A minus U sub B. Okay, so this is the definition for the potential energy. The potential energy, the potential or the difference in potential, as you can see in the given problem what is being asked, is defined by the difference in potential energy divided by the charge from divided by the amount of charge of which the charge experienced this work in moving the charge in from point A to point B. So if we're going to compare this, for example, with the idea of the electric field, recall from our previous video lectures that the definition of the electric field, the measure of the electric field is the measure of the force per unit charge. In the same manner, we could also define the idea of the potential. The potential is symbolized by capital letter V. If the electric field is a measure of force per charge, the potential is a measure of energy per charge. So we have, therefore, by this definition, we have appearing in our numerator the amount of energy, which is U sub A minus U sub B, over the amount of charge, our test charge, which is our proton, Q sub O. So again, let me repeat that. The electric field is a measure of force per unit charge, per unit test charge. Our potential is the amount of potential energy per unit test charge. Force over test charge, energy over test charge. Okay, so knowing this definition, we can now actually solve for the what is being asked in letter C, the potential difference. It is called the potential difference because we basically get the difference between the potentials in point A and point B. Okay, so the corresponding potentials is, of course, the potential at A is V sub A. The potential at B, point B is V sub B. Remember, V and U are different. We refer to U as the electric potential energy. We refer to V as the electric potential, or simply potential. It is this concept of the potential is basically important because from this concept we compound on the idea of having able to produce electricity. Once we will be dealing with more with this idea in terms of the many applications, basically in basic electronics. So the idea of the voltage in basic electronics compounds on the idea of the electric potential. As you can see in the solution, the unit associated with the potential difference delta V is expressed in the units V, which is the units volts. Just like we associate volts with the units for voltage. So basically, understanding the idea of how electricity is being produced using the voltage, that idea is compounds on the basic foundation of the definition of the energy per unit charge basis. Okay, so I assume that you get this. If you're having difficulty again in understanding these concepts, try to review the video lectures again over and over, and I suggest also that you do your corresponding researches and readings regarding this topic. Okay, so I'll be proceeding with the solution. Delta V is equal to, again, delta V is defined as energy per charge. So that is why the form of the equation here is that you have the energy divided by Q sub O. Now, we are asked to get the difference in potential, so that is why we are actually subtracting two values, one from A and one from B. So U sub A minus U sub B. Okay, so of course we know that U sub A minus U sub B is equal to the work done on the charge moving the proton from point A to point B. That is already computed, 1.2 to the negative 12 joules, divided by the charge of the proton, 1.6 to the negative 19. Dividing this two, this gives us 7.5 to the 6 volts. Okay, so this is the answer for letter C. This is called the potential difference. Okay, so what is the significance of computing for the potential difference? So what is basically what is potential difference? Although I have already described to you the potential difference and how it is associated with the idea of voltage, but basically it is somewhat unclear at this point. But let me give you a direct idea of how is the potential the difference in potential works. Okay, so in physics we usually alternate the terms voltage and electric potential difference. An electric potential difference is like a difference in air pressure. No, try to notice or try to recall that when you hear in the news that for example, if during a formation of a typhoon, before a typhoon forms, we usually hear in the newscast that there is a presence, for example, of an LPE. If you're familiar with that, LPE is low pressure area, or LPA, low pressure area. Of course, when you have a low pressure area, of course there are regions in the atmosphere that has high pressure area. If you have a low pressure area, what is usually associated with a low pressure area is that you have a windy weather. So of course, if you have a windy weather and if the strength of the wind eventually develops and increased into a certain level, in a level that is considered a typhoon, then it follows that low pressure area eventually develops into a typhoon. And we hear this during newscast that before a typhoon forms, it usually starts with a low pressure area. Okay, so what is the significance of the low pressure area, and how do we connect this concept with the idea of the potential difference? Okay, so this is the basic analogy. The movement of the air, the natural tendency of the movement of the wind is basically wind flows from a location of high pressure area, moving towards the direction of the low pressure area. So when we say that when there is a low pressure area, wind actually moves from a region in the atmosphere that has high pressure area, going towards the direction of the movement of the low pressure area. And this is the natural tendency of the movement. Therefore, in order for wind to move from one location to the next, there should be a difference in air pressure, high pressure and low pressure. Now, we can make use of this analogy by associating it with the movement of the proton from point A to point B. The natural tendency of the proton to move from point A to point B is due basically because of the upper plate having a positive charge, and this is a positive charge also. So the tendency that the upper plate would repel the proton towards this direction. At the same time that the lower plate is negative, the negative plate would attract the proton, since the proton and the lower plate are of opposite signs. So therefore, the natural tendency of of the proton is for it to move from point A to point B. So this natural tendency is of course is associated with a difference in potential, just like what is associated with the movement of the air, of a difference in air pressure. So since the natural tendency of air pressure is for the air to move from high pressure to low pressure, the same goes with our proton. The proton moves. The tendency of the proton is for it to move from a location, which is point A, of high potential, to a location point B of low potential. So the natural tendency of the movement is for the proton to move from a point of high potential to a point of low potential. Of course, there is a difference in potential between point A and point B. Point A has the higher potential, point B has the lower potential, and the difference between these two potentials, we call this the potential difference, or simply we call this voltage. So that means in order for us to produce electricity in terms of electrical applications, we usually plug in our electrical appliance in an outlet that has potential difference or voltage. Okay, so this is the direct sense or direct application of the idea of the potential difference or voltage. Okay, so we'll be dealing with this further as we go along with our discussion. Okay, so let's go over again with the discussion on work and associated with it with the corresponding increase or decrease in the potential energy and the associated electric potential. Okay, positive charge moving in the direction of or opposite of the electric field. Okay, so our test charge is our proton. The positive charge moves in the direction of the electric field. It is said here that the field does positive work on the charge and the corresponding potential energy decreases. So again, let's go through over this in detail. Okay, so remember our upper plate is positive, our lower plate is negative, and the direction of the electric field in between the two plates would be towards this direction. We know this, that the direction of the electric field is towards this direction. Try to recall in our discussion on the electric field concept that if you have a positive charge, the direction of the electric field of a positive charge is directed outward from the in all directions emanating from the positive charge, and for a negative charge, the direction of the electric field is emanating inwards towards the negative charge. So if you connect between if you set up two parallel plates, one positive and one negative, the direction of the electric field would be towards this direction. Now, since our charge present in between the two plates is positive, the tendency is that the upper plate would push the charge towards this direction, applying this amount of force. At the same time that the negative plate attracts our proton, applying the same amount of force. This is the total force applied by the two plates, and the corresponding movement would be towards this direction. And that force is computed using Q sub O times E. If the charge moves from point A to point B, then the work done is equal to the product of force times the distance. The distance is the difference between the levels or heights between point A to point B. Now, question is in this situation, in this scenario, is the direction is what is the direction between the force and the displacement? Are they in the same direction, or are they in opposition or in opposite direction? Obviously, the force is going downward, and the proton is moves from point A to point B. Therefore, the displacement is also downward. Therefore, the force and the displacement are of the same direction. And try to recall in our previous discussion, if the force and the displacement are of the same direction, what is the sign of the work done? The work done is actually positive. Okay, so, and we have associated that when the work done on the charge is positive, the associated potential energy decreases. Just like what we have already presented, that this location is the location, point A is the location of the higher potential energy and higher potential. Point B is the location of the lower potential energy and lower potential. That means when the object moves from point A to point B, U, or the potential energy, actually decreases. Basically because work done on the charge is positive. The force and the displacement are of the same direction. Now, doing the opposite, if you have the same positive charge, but this time the movement is from point A to point B, the force is still going downward because the upper plate is positive and the lower plate is negative. The force is still downward because the lower plate and the upper plate still causes the object to applies the force downward. But if it happens that the object moves from point A to point B, going upward, then in this case the direction of the force and the direction of the displacement are in opposite direction. The sign of the work done would be negative work, and a negative work is associated with an increase in potential energy. Now, perhaps you're having difficulty in visualizing this, but try this second setup is actually in gravity. This is the situation wherein you are actually throwing a ball, for example, throwing it upwards. Make an analogy between this scenario and an object thrown upward, such as a ball thrown upward. What happens to a ball thrown upward is that when as the object is thrown upward, as the object goes up, the object, for example, moves from point A, which is of a lower elevation, to point B, which is of a higher elevation. The object actually moves upward when you throw it upward. Thus, as the object goes upward, what happens to the gravitational potential energy? The gravitational potential energy actually increases. Since if you recall the computation of the how do we compute for the gravitational potential energy? The potential energy gravity is P is equal to m times g times h, which is dependent on h. So that means the higher the height, the greater the value of the potential energy. So that means as the ball is thrown upward, it actually increases in potential energy, but still the force of gravity is gravity is always working downwards. So therefore, as the object goes up, the displacement is going upwards while the force is going downwards. So therefore, the direction of the force and the displacement are in opposition. The work done by gravity is actually negative. So making that the analogy between gravity and electricity, the force here is like the force of gravity, which is always acting downwards, and the movement of the object of the proton from point A to point B is like the movement of the ball thrown upward. So that means as the proton goes upward, it is actually associated with a negative work, and a negative work is associated with an increase in potential energy. So therefore, point B has the higher potential and higher potential energy. Point A has the lower potential and the lower potential energy. Now, in the second scenario is that instead of having a proton, we have an electron instead. Okay, so we have the same setup. We have two parallel plates. The upper plate has a positive charge, the lower plate again has a negative charge, but this time we have a negative charge, or an electron instead of a proton. Okay, so let's take a look. Look at the scenario in detail. Okay, so the upper plate is positive and the charge is negative. So the tendency between the two is for them to attract. The lower plate is negative and the charge is negative, so the tendency is for them to repel. The overall effect of this repulsion and attraction of the lower and the upper plate forms this amount of force applied on our negative charge, which is computed accordingly by this equation, F is equal to Q sub O times E. Now, if, for example, the charge was forced to move from point A to point B, so what happens here is that the displacement would be towards this direction, and the force of gravity, the force is in opposite direction. Therefore, the work done on the object would be negative. That means the amount of potential energy increases since the force and the displacement are in opposition. In the last diagram, we have the negative electron or the negative charge. Again, this is negative, this is positive. So the tendency is for the lower plate to push the charge, the negative charge towards this direction, having an overall force, combined force of the lower plate and the upper plate towards this direction, and the displacement would be towards this direction. Also, they have the same direction. Therefore, the sign of the work done on the charge moving the charge from point A to point B is positive, and again, the positive work is associated with a decrease in potential energy. Okay, so again, if you're not able to get this the first time, you could always download the video lecture and view the video lecture over and over for until such time that you get the concept. If you're still not able to understand the concept, perhaps you should do your further readings, and perhaps you could look for other videos in YouTube so that you can have a second opinion on this the discussion of this concept. Okay, so now uh, what appears here is the basically the computation for the individual values of the electric potential energy. Remember that in our every scenario we have discussed that the electric potential energy associated with the charge either increases or decreases. So whether it is any of the following setup. Now, what if instead of having two parallel plates, you have as a source of your electric field a single point charge? So instead of having two parallel plates as the source of your electric field, instead of having two parallel plates, your source of the electric field is a single point charge. So the question is, how do we now compute for the associated electric potential energy, and work done? Okay, so let's try to do this using my discussion on this article. So by using an example, okay, so first let us go through with the diagram. Okay, so what we have here is that you have this as your positive charge, and this positive charge is our source charge, and it establishes, as we know, since this would be positive, it establishes an electric field which is directed radially outward in all directions. So at point A, the direction of the electric field of this point charge at A would be towards this direction. At point B, the direction of the electric field would be towards that direction. Notice the difference in the lengths of the arrow. Of course, since point A is closer to Q, the strength of the electric field at point A would be greater than the strength of the electric field at point B. So that is why the arrow representing the strength of the electric field at point A is of greater length as compared to the arrow representing the electric field at point B. Now, we introduce in our scenario our test charge Q sub O, which we move from point A to point B, and our test charge Q sub O is positively charged. So the scenario now here is you have your positive test charge, you have your positive source charge. Since both of them are positive, the tendency is for them to repel. Thus, our Q sub O would be moving from point A if our Q sub O started from point A and it eventually moves from point A to point B. Now, let us try to analyze in terms of work the movement of Q sub O from point A to point B. Um, Q sub O moves from point A to point B, so therefore the direction of the displacement would be towards this direction, along the direction of the dashed line. The direction of the force on Q sub O should be in the same direction, since the tendency is for Q to push Q sub O towards this direction. So therefore, the direction of the displacement is towards this direction. The direction of the force is also towards this direction. Force and displacement have the same direction. Therefore, the work done associated in moving Q sub O from point A to point B is positive. And again, a positive work done is associated with a decreasing potential energy. So therefore, point A is actually the location of the higher potential energy. Point B is associated with the lower potential energy, since the tendency is for Q to push Q sub O from a higher potential to a lower potential. So the next question is, how much potential energy was lost in the movement of Q sub O from point A to point B? Okay, so that amount of associated loss in potential energy is actually computed using this form of the formula. U is equal to K. Remember, this is your constant K. Q sub O over R. How did we arrive with this form of the equation? Let's go through give an example. Okay, so let's have this one. Okay, so recall that work is equal to force times distance, and force for 2-point charges is given by Coulomb's law, which is F is equal to K Q sub O over R square. Now, of course, the distance between the two charges, Q sub O, is represented by D in our formula for work. It is also represented by R in our formula for Coulomb's law. But of course, D and R are simply the same distance, the distance between the points Q sub O. Okay, so since they are the same, we can actually substitute F here in our formula for work. So that means F is Q sub O times D, and since D is R, we can replace D with R. Notice that we can cancel one of the R since this is R square. What happens now is work becomes KQ sub O over R. We cancel one of the R's. Now, in our previous discussion, of course, work is equal to the negative change in potential, which is equal to the negative difference between final potential minus initial potential. Or if we're going to distribute the negative sign, this would be initial potential minus final potential, which is equal to Q sub O over R. Now, of course, if we let the initial potential energy as equal to 0, then our final potential energy would represent the total potential energy. Now, since if we're going to let the initial potential energy to 0, actually this becomes 0 minus minus U, so that means this becomes negative. If we're going to transpose negative sign to the other side, to the side of W, or to the side of the work done, this becomes negative. W is equal to U is equal to K Q sub O over R. So notice that here appears the form of the equation that was presented a while ago. This is U is equal to K Q sub O over R. Remember, our Q represents our source charge, our Q sub O represents our test charge, and R is the distance between Q and Q sub O. Okay, now okay, so I'll be discussing now the sample problem. but I'll be reserving this first on the part 2 of the video lecture.